Okay. I'll leave you the microphone. Well, apart from you have that.
Hello, everyone. I hope the coffee break was good, even a little bit short, but good enough. And we could take some energies to start this third and last block of this morning sessions. This blog is called MySOIL Project and Circular Economy. I'm co-sharing with Fiora Bagnato from Herrero, and myself, that you already know me, Jofre Herrero. And we are going to start with the 3 pilot sites. First, we'll start with the French pilot site, then the Spanish one, and finally the Italian one. So I would like to invite Ilaria, Chicca to come here and join me. And the floor is yours, Ilaria. Or Ilaria, okay. It's co-presented between Caroline Zaoui and Ilaria, both from Novobiom.
Thanks a lot. So yeah, before I leave the floor to Ilaria, who did the work on this project, I take this opportunity to introduce Novobiom. We're a young company based in Belgium, in Wallonia, and yeah, we are experts in fungal biotechnologies, where we use fungi to turn waste into wealth. So very briefly, regardless of the application, we have a vast collection of fungal strains, which we continue to expand and maintain, for which we screen routinely, which we characterized in depth, so that we master their capabilities depending on the application, so be it waste treatment, waste upcycling, or bioremediation. And once we know the capabilities of our strains and that we validated it at small scale, then we produce them at large scale to meet the challenge of large-scale industrialization. So yeah, at the moment we have 300 strains, and we have the capacity in-house to build small pilots for production and remediation. And so very briefly, in pictures, this gives this, and more precisely here, this has been implemented for different bioremediation or mycoremediation soil pilots. And you see the mid-scale, the mid-picture for the production of our inocula. This is also greater details into the process, and which also consists in one of the important points of this project. So to demonstrate that we can scale up the production of the fungal inoculants. So we're here to talk about soil mycoremediation, but the process which I showed you is something we use to serve not only the soil remediation industry, but the cosmetic industry and the waste sector. And because of this process, we recently won the Futurist Fungi Award, which gives recognition to cutting-edge research scientists in the field of fungi research, as well as startups. At small scale, we already worked on other contaminants than the ones that is the main focus of today, chlorinated compound, benzene and PAH, as well as the breakdown compounds of glyphosate. And we also looked at TPH on specific matrix, which were really hydrophobic. So yeah, with this, we are always looking for new types of soil to test contaminants. And yeah, I look forward to discussing further with you about our projects and what we could do together. And now I leave the floor to Ilaria, who is our lead bioremediation scientist.
Thank you. So today we are going to talk about the demo scale for LIFE MySOIL for one site. So LIFE MySOIL is a project that is aimed to demonstrate the mycoremediation at field scale. To arrive to the field scale, we went through to the lab scale, to the demo scale, to the mesoscale, and then to the demonstrator. So we start our biotreatability test by screening our mycobank and also trying different configuration for bulking agents and inoculation rate. By the end of the 4 months of bioavailability test, we found the best conditions to apply for the next scale, which is the mesoscale for 1 ton of soil. There we found, we tried 4 configurations concerning the type of inoculation, so the mixed or the layer, and also the dynamic or the static aeration. So these are some pictures from the mesoscale. And with the best condition that we found in the mesoscale, we went to the demonstrator. That was in July. So we did 2 piles, one bioaugmented and one biostimulated. And in this case, I would like to highlight that the substrate that we used for bioaugmentation was a recipe from our lab that we implemented in large scale, while for the biostimulation we used a substrate that he used for the production of fungi. So most probably we tried to biostimulate also the fungi that were already in the matrix. So regarding the results, from the lab scale, we tried 3 different setups and 5 strains. It ran for 4 months. We achieved 82% of degradation. And what we could see is that the condition that achieved this very high degradation rate was then used for the mesoscale. But we couldn't see really a difference between the control and the treatment. And we used the strain that seems to be the best adapted to the matrix. And in the mesoscale, we used 4 setups and 1 strain, and we achieved 50% of degradation after 6 months. And during this phase, we could see many fluctuations in the 6 months that could be maybe objected to the heterogeneity of the sample, which can be seen in the picture on the right, but also some release of hydrocarbons in the matrix, which was in some way confirmed by leachate results. And in the demo scale, for now, in 3 months, we have reached the 50% of degradation. So for the demonstrator, we observed 2 different degradation daily rates that for biopile were higher than in the mycopile, and in the mycopile for now we are reached, we are slightly below the legal threshold, and but with the biostimulated thesis, we reached higher daily rate TPH degradation. And we could see that at T2, we saw a release of hydrocarbons, and by statistical analysis, we could see that the higher fractions of hydrocarbons were the most released, and a difference between mycopile and, the bioaugmented and biostimulated piles was seen for the bioaugmented pile. And we monitor different physical parameters in the 2 different sides of the pile, the middle and the upper layer, in 3 different points. Humidity is very important to monitor because with the type of soil that we have, we could see that in demo scale, in the mesoscale, we arrived to a certain point that the humidity was too high and too sticky. So we monitor that this parameter very closely. And so far, except few peaks, we didn't see nothing worrying. And it's also important to monitor for oxygen levels, because then we can see if oxygen level is too much, but in this case, it's not. And electrical conductivity more or less follows the humidity trends, and we are below the threshold of 4, where is the salinity threshold. So we are kind of fine for that. For the temperature, we actually faced a very high peak at the very beginning, since the aeration was not working and it was summer. And then basically we went down to between 30 and 40 degrees, which is seen from the lab experiment that pleurotus is still vital at those temperatures. And for the gas analysis, what we can see is that the oxygen was never really a limiting factor. And the most activity was shown around August. And we can see also some methane and sulfur production, especially in the biostimulation pile. Concluding, what we can say is that we actually validate the production at large scale, and a validation, also implementation of a demo scale. And after 3 months, we could reach a legal threshold, and we could go below the legal threshold. And based on the daily depletion rates, we could go after 6 months around 500 ppm. And for the biostimulation pile, we could reach around 600 ppm. And we still face some fluctuations, and that might be the reflection of release of hydrocarbons, especially for aliphatic and aromatic fractions. So actually this is our, now it's our starting point to actually go further. At the beginning we tried 70 strains as we had in the mycobank, and we are going to screen even more until 300, most probably even more later. And we are trying to even considering some other strains that are not basidiomycetes strains, and the production, to upscale the production for those strains, but also finding some the best conditions to grow for basidiomycetes, meaning that they might need some other growth conditions for TPH degradation, and but also we need to fine-tune the synergy between the bioaugmented strains and the microbial community that is already there. That is really important to achieve even better results. And for that, we need also some other tools that are mostly modeling and metagenomics, and to find other way to make biotreatability, to follow up really what is happening already from the biotreatability, and to utilize for the upscaling. And this is our team. Thank you for your attention.
Thank you, Ilaria and Caroline, to stick in time, because we asked these three presentations to keep it into 15 minutes in order to have the schedule that we were planned to do and have some time for the open discussion. I would like to remind the open discussion will be held in person, but also the people that are virtually viewing this open day can write the questions into the chat, and our colleague, Ivan Garcia, will also let you step in. So now we are moving to the second presentation held by Jorge Diamantino from Kepler and Rafael Antón Herrero from Universidad Autónoma de Madrid. I presume that they are starting, Rafael is starting, and then Jorge will step in.
Well, thank you. I will start to talk about the Spanish approach to this project, the MySOIL. This one. Okay, I will start to present really briefly the Autonomous University of Madrid. We are a really big university established in 1968. We are composed of 8 faculties, 64 departments. Also, we have more than 30,000 students. And in talking about research, we are part of the Department of Agricultural Chemistry, and we are the group, the research group, called Sustainable Agro-Environmental Innovation. So the first point is that we, as a research group, we really believe in applied science. So that's why we joined this project, MySOIL, because now we also have embraced the word transfer, which is a really important word. And also, we do believe that transfer requires scalability, another really difficult word to work with in science. For example, the first point is where we get the soil, our real soil. We get it from Cepsa refinery in La Rábida, which is in Huelva, it's in the south part of Spain. And also, when we arrive there, they have 2 big piles of 90 cubic meters each one. The first point is like we have to combine both piles just to get enough soil to continue the experiments. So we did that homogenization of both soils, pile 1 and pile 2 that I showed you in the pictures. When we have mixed that, we just get a portion of 10 cubic meters, and they send it to the Autonomous University to start to do the several laboratory experiments that we started doing. From the point of view of science, the first point is that we have the different piles, they have different concentration. So we have to remake all the analysis after the both piles have been mixed. The texture in the project we just saw is really important. In our case, it's a sandy soil with 90% of sand, which is really sandy soil. And it means that we have not faced problem of aeration, but we are facing problems of keeping the humidity. So that is the main point that we are reaching in this project, that the texture of the soil is more than important. It's a key factor that it should be taken into account. The strategy, the WAM strategy, the Spanish strategy, we are going to use a spent marrow substrate, which Tatiana just told in the previous presentation. It's a waste in the point of view of industry, and it's called spent because it's no longer profitable for industry. It not means that it still contains fungi that is alive, but it's not profitable enough to make mushrooms for the commerce. So that's why it's called spent. But it's a waste, yeah, from the point of view of the commerce, but from the point of view of science, bioremediation is no longer a waste. Also, we have started, and that is where the word scalability comes into play. We started with 4 different spent marrow substrates at the laboratory scale. I will not, on this presentation, I will not put any data about our laboratory scale because this is a demonstrative project. And we just erase Pleurotus syringae and Pleurotus erodi from the equation. Why? Because in Spain, they are not producing enough just to make that spermatus an alternative. Simple as that. On the laboratory, 4 of them were really good. On the field scale, only 2 of them, which are going to be Pleurotus striatus and Agaricus bisporus, are produced enough to be considered a valuable alternative. Then our design of the mycopiles, we just established several mycoreactors with an airflow, which is the airflow is made by aspiration, and all the mycoreactors are being watered. Why this picture? Because for us, the soil reception, we as a university, we have always worked at the laboratory scale. So for us, receiving 10 cubic meters of soil was a new step so that's why you will see a lot of pictures in my presentation. The spent marrow substrate sampling. We just, for this project, for the mesoconspan part, we used Agaricus bisporus, Pleurotus striatus, and we just added a new treatment that is called non-inoculated Agaricus bisporus substrate. This is the substrate used by the companies before the inoculation of Agaricus bisporus. It's not spent, and it's not a waste, but we use it as a control just to see, and I will just say before in the results, this is other control that we added in our mesocosm. Now, the mesocosm preparation. We have to homogenize all the soil with all the spent marrow substrate. That we did it manually was a really interesting task done at university, but things of scalability and to demonstrate technology. Then the mycoreactor setup. Here, as you can see, we just added at the bottom as a layer just to avoid the water being there and to just provoke problems. And also we added the different layers of the spent marrow substrate, as you can see in the pictures. We have included also several sensors just to control the oxygenation, the electrical conductivity, the watering, the soil moisture, and the watering was done by drippers, as you can see in the pictures. We have also installed the MYCOTRAPs, which is another part, which I'm going to tell my colleague, which is another part of the project. And, well, I just leave it here just to introduce where and when MYCOTRAPs were introduced in our mesocosm. And now, the important part, the treatments. We just work with 5 treatments. The first one, the S alone, is soil control. Then the SA, which is soil plus the spent marrow substrate Agaricus bisporus mixed. Then the SAC is called the contingency treatment. Why? Because if the SA do not function, we should add another contingency treatment, which in our case will be the additional surfactant. I will demonstrate technology that is being used. Also, the SS treatment is the soil plus the Agaricus bisporus substrate non-inoculated, and the SAP, which include a layer of Pleurotus striatus. That treatment, the SAP, combines 2 different spent marrow substrates, the Agaricus bisporus and the Pleurotus striatus, in layer, the Pleurotus striatus, as you can see in the different pictures. We have, in our contingency treatment, we have added surfactant addition in a small concentration of 0.1 kilogram per kilogram of the soil. Then, as you can see, we have monitored the different parameters, and you can see the surfactant addition, because when we added the surfactant to the other treatments, we added water just to keep all the moisture done and keep it in the same place. One point is that when we have added the substrate, we keep the moisture in the soil. So that is the first point. If we add a substrate, it's a way to keep the moisture in the soil and not to have to water in all the different biopiles, because this substrate is keeping the moisture of the soil. Then also we have the electrical conductivity, the soil temperature, and the oxygen concentration of our different mesocosm treatments. The TPH removal at 90 days. From here we extract two main results. The first result is that our soil did not contain a really long chain aliphatic compounds. All the compounds were really were lighter TPHs. But the two main things that we get from this result is that, as you can see, the higher concentration was get in the SS treatment. This treatment at the beginning do not contain any fungi, because it was non-inoculated agaricus bisporus. At the end it contains, just because cross pollution between treatments. So it means that the soil must be amendment, with a good amendment, the soil is able to degrade it by a consortium degradation combined the fungi and the autochthonous microbiota. Another point we get is that if we have the surfactant is able to mobilize the compounds. That is, we have not proved, but we have proved is that with surfactant we have a higher degradation of the TPHs. Then we have also analyzed the metagenomic data of all the mesocosms, and when we get is that when we added Agaricus bisporus and Pleurotus asperatus spermarrow substrate, we saw that several hydrocarbon degraders, their abundance increased. So here is the synergic effect of. We have also experienced what was said before, that persistence of the fungi inoculated at the beginning is not the best. But at the end, if the hydrocarbon concentration goes lower, you know, is what matters at the end. And that is also other pictures about all the MySOIL Life team from the part of the university. And now Kepler will continue with the next steps of the project.
I'll wait for my presentation. Okay, I'm Jorge Diamantino from Kepler. I'll start presenting my company. Kepler is an environmental consulting company with 28 years of experience. One of our services are, of course, the soil and groundwater decontamination, where we use often the bioremediation technique. We also perform inspection of contaminated soils and groundwater. We are a certified company to do those inspections. And another service that we have is to act in urgencies. So when there is an accidental spillage, when it occurs a spill, we act in less than 24 hours to contain the spread of the contamination. Another line of business in our company is the biogas plants. We perform the design, the building, and the operation of these plants to produce methane or electricity. Then we also have our own laboratory where we perform microbiological analysis using molecular biology tools like NGS and qPCR. And we also perform biotreatability assays in different metrics in order to choose the best treatment strategy. At last, we have a research and development department where we participate in R&D projects like, for example, MySOIL. So we are participating in LIFE MySOIL. Our task is to build the full-scale mycopiles in CEPSA's refinery. CEPSA, as Rafael said before, they are providing us the soil and the place in their refinery to build the mycopiles. So after the mesocoms results, what we decided to do in the full scale is this. We will do the treatment of the soil in two phases. First, we will build dynamic biopiles in first phase that will last 2 months. We'll build 2 biopiles, one control with just the soil, where we'll perform where we add water and aeration by turning over the soil, and then in the mycopile, first we'll mix the soil with the substrate non-inoculated, without fungi. This is to biostimulate the autochthonous microbiota of the soil in the first month. After 1 month, we'll do a turning over of the soil and provide more water if necessary. Then, after 2 months of this biostimulation, we'll change to static biopiles, where we'll connect to a treatment plant, the biopiles. So at this point, we'll add a surfactant, because we saw in mesocoms that it helped to decrease the TPH concentration by making the TPH more bioavailable. And in this point, we also will add the fungi with the spent mushroom substrate of Agaricus that will be mixed with all the soil. And then we'll put a layer in the middle of the biopile of Pleurotus austriatus. So we already started building the biopiles last week, and I hope to finish them soon. So this is some pictures from last week. This is the site where we'll put the mycopiles, and I hope in the future we have some results. Okay, thank you.
Thank you. And now I would like to introduce Rachele. Rachele from Rewind, who will present the results of the pilot sites here in Italy.
Good morning. I will present the mycopiles in Italy in collaboration with the University La Tuscia. As we said before, the MySOIL project is divided in 3 phases. First of all, we have the phases of the biotraceability test that were performed in University of La Tuscia, in the laboratory of the University of La Tuscia in January 2022. And the pilot test in November of the last year on Ferrara site of Herrero with the mesocosm reactor with 1 cubic meters. The soil that we use for the first 2 phases is a soil coming from a gas station contaminated by hydrocarbons. So this for the last phase, the phase of the full-scale pilot test in a treatment plant, we use another soil, and we sampled the soil in October, and we set up the test in November, in this month. Now we analyze the characterization of the soil for the first 2 phases. We have that the soil that we collected from Borgofite is a soil with a starting concentration of 7,000 micrograms per kilograms. And as we said from the granulometry analysis, is a silty and clay soil. First of all, we now analyze only the phase of the mesocosm, and we will see only the design and the results of the mesocosm phase and the design of the full scale. First of all, we have the pilot plant design. Oh, sorry. Here we have the pilot plant design and the realization of the pilot plant on a site owned by Rewind in Ferrara. And we have the plant consisting of 7 cylindrical reactors that are equipped with the insulation system, an heating system, and also a temperature sensors. Also, we have an irrigation system, an humidity sensor, and a collection, a system that collected the excess water from the plant. Finally, we have also the aeration system. This aeration system worked in a depression mode. And we have also the treatment of extracted air from the plant. Here we have the soil preparation before the setup of the mesocosm. We originally, with starting point, we removed the pebbles from the soil. As second activity, we mixed the soil with the 8% of sand, and we corrected the humidity to 70%. After this, we mixed the soil with a bulking agent in a straw soil mass ratio maintained less than 12%. This allows us to increase the matrix porosity and also the aeration of the soil. As we said before, the Smilot plant construction, it was in October 2022, and the duration was of 6 months. In fact, we finished the test in May 23. Here we can see a scheme of the setup of the mesocosm, and we have 2 different configurations. First of all, we use the fungal inoculum for 2 of 7 mesocosms that we can see here, and for 4 of them we use the spent mushroom compost. And finally, we have the last one, that is our control mycopile, without inoculation. Also, we have 2 different configurations for our mesocosm, the single layer configuration, and the second is the multiple layer configuration. We use the multiple layer configuration to allow the contact between the soil and the compost, to have a more homogeneity and more representativeness samples. Here we have some operating parameters monitoring. First of all, we have the 3 different probes at 3 different depth level in the mesocosm. We have the humidity and the temperature probes, and they automatically adjust the irrigation and the heating inside the mesocosm. We also set up the temperature, the humidity, and also the oxygen maintained highest than 16%. We also added in a few weeks nutrients as the phosphorus, and how we can appreciate from the graph here, we have that in the first few weeks, the temperature increase due to the initial metabolic activity, in particular in the EF1 and EF2 mesocosms, that are the mesocosms that was constructed with the fungal inoculum. The peaks up to reach a temperature of 40-45 degrees. First of these peaks, in this picture, we can appreciate the presence of mycelium in EF1 and EF2, but after this peak, we are not able to see the presence of mycelium. Here we have the soil sampling campaign. We divided the times of sampling in 3 times. And we can see what happened in our reactor. First of all, in the first 3 months, in all of these tests, there was a natural compacting of soil from 70-75 centimeters to 45-55 centimeters. And we can say also that at time T1, we have the presence here in the picture. We have the presence in the CS2, that is the mesocosm with the spent mushroom compost. We can see the presence of the Pleurotus striatus. But after this time, also in this mesocosm, we are not able to see the presence of mycelium. This is probably because there was a compactation of the soil, and this does not allow the growth of the mycelium inside our mesocosm. Here we can see some different results about the hydrocarbon degradation in the soil fraction less than 2 millimeters. we see that for the CS1, that is the, I remember you, that is the spent mushroom compost mesocos, we have that it show the lower concentration, but all of these mesocos are a similar trend as the control mycopile. From the table, we can see that the best degradation rate is for the CS1 up to 70%. And finally, we can appreciate from the chromatographic analysis that for all of 3 times of sampling, we have that the most degradable fraction is the fraction C8, C19, here in particular in T2. Now we can pass to see the microbial analysis, and first of all we analyze bacteria and fungi. For the bacteria, we can see that in all mesocos they increase after 3 months to reach the plateau, with the exception of the EF2 that increase also during the last quarter. For the fungi, we can see that we have a strong increase after 3 months, and only that they increase also after 6 months are the F2 and the CS2. Finally, we can see the right part of the graph for the cultivable bacteria specialized in degradation of alkanes and polycyclical aromatic hydrocarbons. And for both of them, we can see that for CS1 and the control mycopile, we have a strong increase after 3 months. For the real-time PCR, we have results very, very similar to the, in terms of abundance of 16S and 18S genes. For this part, we analyze enzymatic markers of microbial activity, and also the bacterial and fungal genes abundance after 3 and after 6 months. For the enzymatic markers, we analyze 2 enzymes. For the first enzymes, we can see that for the EF1 and CS1, we have a strong increase after 6 months of them. And for the dehydrogenase dosage, we have a drastic reduction after 3 months, and an increase only in EF1 and EF2 and CS1 after 6 months. For the now we can pass to analyze the Illumina method. We can see from the picture the Illumina results are after 3 months of test, and we can appreciate the presence here of the Pleurotus striatus in CS2, and this confirmed has the presence of the Pleurotus striatus as I showed you before in the imaging. And also the presence of the here of the thermophilic fungi in EF1 and EF2. Now we pass to analyze the last phase that we will see today in the afternoon in the plant. For the full scale, as I said before, we collected another soil coming from Cigliano, that is a municipality near Milan. And this soil it has a granulometry, more sandy granulometry. And with a starting concentration around 2,000 micrograms per kilograms. We are attending the results about this. For the full scale, we set up the 2 biopiles in the treatment plant called Trimper, and we set up 2 mycopiles of 50 cubic meters each. First of all, we set up the biopile, that is our control, the biopile only with the contaminated soil. And the second is the mycopile, a pile with the contaminated soil amended with spent mushroom compost. Here we use the Agaricus bisporus compost and also the Pleurotus striatus. We added Agaricus bisporus after the result that we analyzed also from the test of the other partners, and also because the Agaricus bisporus can help us to increase the porosity of the soil, and because it's in a loose form. The monitoring activity of the tests are divided in 6 times, and we will monitoring interstitial gases and hydrocarbon content, and we will use the same methods that we used in the mesocosm. Here we have the setup that we did this month in Trimper, and first of all we mixed the soil with the Agaricus bisporus with 3% by weight. After this, here we have the picture of the formation of the pile and the length of perforate pipes. One pipes at 0.5 meters from the ground, and the second from 1 meter from the ground. This helps us to ensure the inadequate ventilation to the system. Okay, here we can see other picture of the formation of our biopile. First of all, we have the first layer, that is the layer of the soil with 0.5 meters. The second layer is the layer of Pleurotus striatus that is 30 centimeters. And after we have another strata of soil, Pleurotus and soil. Here we decided to improve the centimeters of the Pleurotus striatus to avoid the compactation of the soil. Before in the mesocosm we used 15 centimeters, here we used 30 centimeters. And finally we have the last imaging of the treatment plant with the final configuration of the mycopile and the biopile that we will see today. Thank you.
Thank you, Rachele. As she said, what Rachele told us, we will see in this afternoon in the plant. I take advantage of this moment to take Trimper, the treatment plant where we built the mycopiles and all the staff for the help and the professional they put in this project. And now I present our MySOIL colleague Anko Fischer from ISO-Detect, who will speak us on innovative tools for biostimulation evaluation. Thank you.
Thank you. And yeah, as Fiora mentioned, I'm Anko Fischer from the company ISO-Detect. ISO-Detect provides innovative tools for environmental forensics and for evaluating natural and stimulated degradation of pollutants into the environment, mainly at contaminated aquifers or contaminated soil. Beyond this, we work also in the field of hydrogeology, hydrology. We provide analysis of isotope and anthropogenic tracers that can be used for investigating the interactions of surface and groundwater or between different aquifers. And we do there also groundwater age dating. But now I will come to the topic of today, which are a device, it's called MYCOTRAP, and this is be used for evaluating the biostimulation in soil. The basic principle of this MYCOTRAPs is, as you know, the petroleum hydrocarbons consists mainly of carbon, and there are 2 forms of carbon. There are 2 stable isotopes. The one stable isotope is the 12C with a mass of 12, which is the most abundant carbon isotope in nature, and the 13C, which is the less abundant stable carbon isotope in nature. And what we can do here, we can artificially label a specific compound with the certain C, which you can hear. And this certain C labeling can be used then to follow the certain C label into mineralization products, in metabolites, or in the biomass. So what is the concept? Using this the basic principle, here we have a device where we add the certain C label target compound. We install this into the soil for several weeks so that a microorganism can colonize on this. And if there are microorganisms that convert the certain C labeled compound as a carbon source, you will find back the certain C into biomarkers. And there we use a very sensitive tool which is called compound-specific stable isotope analysis, where we data mine the ratio of the certain C and the 12C carbon. This is actually used to measure differences in the natural isotope abundance of carbons. So, as I mentioned, we are here very sensitive to investigate the certain C incorporation. So what kind of biomarkers are available? We have here the fatty acid, or better also the phospholipid fatty acids, which are main components of the cell membrane. We can follow it, the certain C labeling, into amino acids, which are main components of proteins, and also following the certain C label into the RNA or DNA. So first, for us, we did a selection of the biomarkers, what we want to use. We have here the amino acids. The extraction and analysis is manageable with manageable effort. And however, there is a very limited taxonomic information from the amino acids. So the phospholipid fatty acids, they are also the extraction and analysis of them is combined with a moderate effort, and you get also moderate taxonomic information. And for the RNA and DNA, extraction and analysis has a relatively high effort, but you get comprehensive taxonomic information. So for us, we go the middle way there. Of course, the others are not excluded. If interest, it can be also used, but we go the middle way. We use the phospholipid fatty acids. As I mentioned, these are main components of the cell membranes of the microorganisms. So which kind of devices we figured out? We have two devices. They are approximately 5 to 6 centimeters. We have stainless steel cartridge and a Teflon cartridge. And what kind of matrices we want to investigate or we selected? This is on the one hand side a biocoal and soil from the field side. So why the biocoal? We have experiences there for similar devices where the microorganisms colonize very well there. And so we can create a MYCOTRAP which is relative comparable for different situations, because the soil varies, the conditions and the texture of soil varies between different soils, so they are relatively specific for the field site, and comparing this between different field sites is then not so easy. So we select as a target compound a hexadecane. That means the certain C-labeled hexadecane. So, and these devices we tested in different combinations during the mesocosm experiments in Italy and in Spain. Now I want to present mainly the results that we get from the mesocosms in Italy. On the upper part, or here you see the phospholipid fatty acid profiles, what we get from the Teflon micro traps with soil. On the upper part, you see the results of the inoculated mesocosms, fungi inoculated ones, and here the control. And there we get this pattern. They are quite similar. The fatty phospholipid fatty acid pattern between the inoculated and the control ones. And there we investigated then also specific phospholipid fatty acids which are specific for bacteria and fungi. And we saw there, when we just take the zoom out of the 16C phospholipid acids and the C18 phospholipid acids, that the amount is relatively similar there. So now coming to the pattern of the stainless steel microtraps, also there we see from the inoculated ones and the control ones, we see quite similar phospholipid fatty acid pattern there. So, and now coming to the biocoal, here we just investigated the controls, and we see here that we have quite strong problems to get the phospholipid fatty acids back from the biocoal. So at the moment, it's mainly the reason that they stick too much at the biocoal. So we've tried to solve the problem with a better extraction protocol, but for the moment, the biocoal seems to not suitable to use them for the microtrap approach. So coming to the certain C enrichment, first introduction how to, what is the unit there? This is the so-called delta notation, which means that you have this, the ratio of the certain C to the 12C from your sample compared to an international standard. And because this is very small, you normally under natural abundance, you provide this in per mil. Why you use this approach? Because relatively differences in the isotope ratio are more easier to measure than the concentration itself. So what you see here, there are results from the mesocosm test with the Teflon cartridge with soil. And here you see the delta certain C value of the phospholipid fatty acids at a specific retention times. And there, normally the natural isotope abundance of phospholipid acid range approximately between -35 up to -10 per mil. And what you can see here already at the scale, we are far beyond from this natural abundance. It means we have here enrichment of the certain C in nearly all fatty acids that we found extracted from the Teflon cartridge with the soil. So that would mean we have a successful proof of certain C decaying mineralization there and incorporation of the certain C from the hexadecane into the phospholipid fatty acids. And the other thing is we have a successful validation of the microtraps using Teflon and soil as MYCOTRAP prototype. Here you see the results from the stainless steel cartridge with soil. Again there, here you see the phospholipid fatty acids, carbon isotope ratio, and again there they are significantly more positive than natural isotope, carbon isotope ratios of under natural abundance. And so here again we have also a successful proof of complete hexadecane biodegradation of the certain C, and this incorporation into the phospholipid fatty acids. And again there, this is also a successful validation of this type. That means the stainless steel cartridge together with the soil. So coming now to think that we investigated for the mesocosm test in Spain. Petroleum hydrocarbons consist not only on carbon mainly, but also on hydrogen. So what you can use instead of certain C-labeled compounds, you can use, coming shortly, also hydrogen has two stable isotopes. The isotope with the mass 2 is the rare isotope, and the most abundant hydrogen isotope is with the mass 1. And what you can do, you can artificially label organic compounds with the hydrogen with the mass 2, which is also known as deuterium. That means deuterium labeled. And what is the benefit for this? They are significantly less expensive than the certain C-labeled compounds, and you can commercially get significantly more compounds which are deuterium labeled compared to the certain C-labeled ones. So, and we made there also a test. We installed MYCOTRAPs with deuterium labeled hexadecane, as I mentioned in the mesocosm experiment in Spain. And just to show it here, this is a chromatogram in the upper part of the phospholipid fatty acid standard. That means with natural abundance. Here, these are the different phospholipid fatty acids as peaks. And below you see an example we investigated. We had 3 MYCOTRAPs installed with the deuterium labeled hexadecane. They look nearly similar. And here you have one example from the inoculated, with fungi inoculated mesocosm. And in brown, you see the mass trace for the hydrogen with mass 1. And the green line shows the mass trace of the deuterium. And what you can here see, you see significantly peaks of the green line, which means this indicate a very strong deuterium enrichment into the phospholipid fatty acids. So we have here a strong deuterium enrichment in the phospholipid acids. This proves the degradation of deuterium labeled hexadecane. So we have here the potential for cheaper MYCOTRAPs, which are available for more target pollutants. So coming to the conclusions and the outlook, so we could show that different MYCOTRAP prototypes with Teflon and stainless steel, as well as soil as matrices, could be successfully tested. The prototype test with the biocoal was not so successful. We try to see if we can improve the extraction protocol of the phospholipid fatty acids from the biocoal. Besides MYCOTRAPs with the certain C-labeled target pollutants, there is a high potential for MYCOTRAPs with deuterium labeled target pollutants as a cheaper option and for a higher variety of compounds. And the next steps are that we test our MYCOTRAPs in the mycopile experiments, in the pilots. In France, we installed them already and they will retrieved soon. In Italy, they will be installed, I think, in the next days. We are preparing at the moment in our lab and will send this to Italy. And we have already planned also the installation of MYCOTRAPs for the mycopile test in Spain. So thank you for your attention.
Thank you very much for your work too. Now we will have a question and answer session. chaired by... Now, we will have our colleague Carlos Garcia, who is connected from the University Autónoma of Madrid, who will speak us about the microremediation, scale-up, and circular economy, lessons learned, and future steps.
Thank you.
Please, Carlos.
I have to share my screen. Oh, okay. Okay, thank you. Well, first of all, sorry, because I would like to stay in Milan, but unfortunately I can travel this time. Well, how can I pass the slide? Okay, thank you. Okay, microremediation is an emerging technology, biotechnology. We're talking all this morning about this, but this time is not employed at full scale. There are many experiments at different scale. Some of them have a lab scale or some pilots, but it's not implemented at industrial scale. There are different pollutants focus in microremediation. MySOIL focus on TPAs, but there are many experience on polycyclic aromatic hydrocarbons or PCBs. But we have to perform this scale up. So the objective of MySOIL is the demonstration of microremediation to remediate industrial soils contaminated with TPAs and validate the technological implementation of this biotechnology at industrial scale. We have to solve several challenges, such as the logistic and the necessary equipment specific for microremediation. An important point to solve is the production of fungal biomass, and above all the production of fungal inocula to colonize the soil in large quantities. Next, please. Okay. Here you can see the different steps of the project. First of all, investigation of the site, pollution characteristics and pollution concentration, kind of soil, climatic condition, and so on. Then we perform a different biotraceability test to determine the selection of the fungal species and the inocular ratio, inocular soil ratio, for instance, or the kind of material of substrate to inoculate the fungi. And then we are in this step in the full scale validation. To this we perform different scales, mesocoms, where we scale up from 1 or several kilograms in the biotraceability test to 200 or 1 ton of kilograms of soil. And then finally the pilots, the biopiles of 50 cubic meters. To this we have to produce some knowledge of the management of the pilots of the mycopiles. For instance, how to mix the soil and the mushroom. For instance, in the last chats we discussed about layers or mixing soil with the mushroom inocula. Next, please. Well, microremediation demands specific conditions to assure fungal colonization of the polluted soil, survival, and of course, pollutants removal. It's necessary high soil moisture, but not excessive, to find an equilibrium between water and oxygen. high porosity and low compactation to assure aerobic condition. This is a key point. It's necessary oxygen in this biotechnology. It's necessary a source of nutrients and carbon, nitrogen and phosphorus as major nutrients, temperature control, and there are specific managements for mycopiles because fungi produce networks of mycelium, and we should not destroy during the mycopile, during the treatment. Hence, static biopiles seem more adequate than dynamic biopiles for this specific management of mycoremediation. To the zinc biopiles with high porosity and assure aerobic conditions, the use of aeration system and bulking agents is very interesting, and it's a good solution to assure soil aeration and low compactation. And moreover, biopiles of low dimension to minimize the possible compactation of the pile. Next, please. Okay. Well, in the consumption in MySOIL project, we use two different approaches to inoculate fungi, spent mushroom substrate or specific strains in specific mediums. Universidad Autónoma de Madrid and Kepler are investigating about the use of spent mushroom substrate. Novobiom and Belguim use specific strains and specific substrate, and Unitus and Enani Rewind explore both strategies. Well, next, please. Well, one important point in mycoremediation is the use of bulking agents and inoculum media, because we have to assure aerobic conditions and potent, very strong inocula to assure the colonization of a difficult media such as this depolluted soil. So we can extract some lessons from the nature and the mushroom industry to explore the mycoremediation. Well, fungi plays a major role as the composter and recyclers of organic matter in nature, so we can mimic the habitat of fungi to favor the fungal colonization. To this, we can use the knowledge of the mushroom industry using selective media and reusing local waste. The most popular ways to produce mushroom substrate for the crop of the mushroom are cereal straw, cob corn, or pruning waste. But the question is, next please, are organic or are not organic waste? Because all of these materials could be agricultural waste, but at the same time is the raw material for the mushroom industry. Even the spent mushroom substrate, the substrate after the culture of the mushroom, could be included in this cycle to produce new substrate for production of mushroom. Next, another one. Okay, thank you. And this is a point where the circular economy and mycoremediation are very close. In this slide, you can see the aspect of two of the most popular edible mushroom, Agaricus bisporus and Pleurotus ostreatus, and the aspect of their substrate. The substrate of Agaricus bisporus is a compost produced with wet straw and manure composted, because Agaricus is a secondary decomposter, and in the case of Pleurotus ostreatus, the necessities is different. It's a primary decomposter, and the substrate is only wet straw. This is very important because we have to select adequate food or adequate substrate for each fungi. And this is key to develop a good colonization and a strong inocula for the soil. In the case of spent mushroom substrate, the fungi is, the mushroom is alive. You can see here the aspect of the spent mushroom substrate where the mycelium is alive, and we can use this substrate, this spent substrate as inocula for the soil. Next. Okay. The question is, spent mushroom substrate is a waste or a raw materials, and this is a key concept of the circular economy. Spent mushroom substrate are organic materials with very interesting properties for mycoremediation because they have a low density and high porosity, so are good materials as bulking agents and materials to improve the water retention capacity of the soil. And this is key points in mycoremediation. Are lignocellulosic materials, so contains nutrients for the mycelium to help in the colonization of the soil. The own mycelium of the spent mushroom substrate is alive, and we can use these materials for inoculum colonization, and contains indigenous microbiota that can help in the bioremediation of the polluted soil. And a very important point for the industry is an abundant subproduct and is really, really cheap. So spent mushroom substrate are useful in mycoremediation. It's an alternative to the linear economy and can be a bioresource and not a waste. Next. Here you can see some examples of soil colonized by spent mushroom substrate. In the slide of bioavailability test, pH plus lead is a soil polluted with polycyclic aromatic hydrocarbons and lead, colonized by Agaricus bisporus, inoculated from the spent mushroom substrate. The other photos are experience of the LIFE project, is the soil from Huelva, and one slide is the use of spent mushroom substrate from Agaricus bisporus, and the other one is the aspect of the soil in the first step of the colonization by spent mushroom substrate of Pleurotus ostreatus. Next, please. Okay, but in the case that we would like to use a specific strain and specific substrate, we have to be able to produce this inocula, this mushroom, this substrate at enough amount to be used in mycoremediation. Next, please. To this, we can explore the know-how of the mushroom industry because they have all the knowledge to produce these materials. It's necessary to produce high amounts and regular amounts of mycelium and mushroom substrate, and this industry works in this point. And in addition, we can, in mycoremediation, we do not need the production of the mushroom. We only need the production of the mushroom substrate, the colonization of these materials, and with these materials we go to the biopile to colonize the soil. Next. Well, here there are some photos and one video. Next slide, please. Of the manipulation of the substrate to inoculate grain from a spore. The substrate is free of potential pathogens to fungi or different competitors. and is inoculated with seed colonized with the mycelia of the selected strain and the selected fungi. And then the material is incubated under controlled conditions, mainly temperature and humidity. Mushroom industry offers very good opportunities to produce fungal mycelium and substrate for mycoremediation. In addition, many of the fungi used in mushroom industry are basiomycetes, and this industry is expert in this the production of this kind of fungi. And some of the species of fungi used for mycoremediation are basiomycetes. So it's relatively easy to find a specific substrate for a specific fungi in the case of mycoremediation. But there are some limitations. For instance, ascomycetes are good options for mycoremediation, but in general, these fungi are pathogens or contaminants of the mushroom industry. Next, please. So our project, MySoil, the objective of this project are in line with the further steps of mycoremediation and tries to clarify some challenges of the mycoremediation. This biotechnology needs guidelines for the implementation of this biotechnology. It's necessary to test this biotechnology at full scale and to determine clearly the key points of this process and the management of the mycopiles. Another important point is the replicability of the mycopiles in different contaminated sites with different soils, climate conditions, pollutants characteristics, and of course TPH concentration. For instance, in this project we are testing 3 different sites and we are looking for additional soil to replicate this technology in other places. And finally, MySoil is focused on TPH, but this biotechnology can and must be applied to other contaminants to expand the use of mycoremediation. In this project, we are going to test the remediation of soil polluted with heat thermal fluid used in solar thermal plants. And these fluids are mainly biphenyls and other organic or aromatic pollutants. And this is all. Next. Thanks. Thank you very much for your attention.
Thank you very much, Carlos. So now we have a question and answer session chaired by Laurent from Valgo, Laurent Tamberger, together with Ivan Serda, who is connected from Eurecat and who will manage the remote questions.
Thank you, Fiora. Because I don't have the opportunity to ask a question directly during the coffee break or during the lunch, we will start with online question. Ivan, if you hear me, maybe...
Yes, can you hear me?
Yeah. Yes, you may read the first question from the chat.
Okay, we have a question about the presentation of Tatiana Stella in the first block. Laura Canonica from the University of Genoa wants to know what was the concentration of the fungal inoculum that was used in the last experiment she presented. So maybe we can go back to her presentation and check that slide.
Well, your sound is not stable. Maybe you have to repeat because Tatiana didn't hear the question. Yeah.
Okay. Yeah, the question was what was the concentration of the fungal inoculum that was used in the last experiment she presented?
Yeah, sorry, it's working, yes. It was 10% in volume, I'm speaking.
Okay, yes, we can hear you. Perfect. So for now, is the only online question that we have. Maybe you can go for
Yeah,
the
maybe
questions
they will
in
be
the room.
stimulated by the question on the
Then at the
room.
end,
So,
exactly.
who is first in the row to ask question?
Thank you. Actually, I have a general question for the MySoil team members. So we have learned today that fungi has a great capabilities and potential, and also the application in mesocoms and pilot are really good and great. But mycopile still stand a step behind the biopiles in terms of scalability. Indeed, biopiles treatment plant are quite widespread in Italy, also in Europe. So my question is, which are the obstacles that you are trying to break and to overcome with your project to bring the mycoremediation at industrial scales? It's only a technical issue or economical issues or both? Thank you.
I may start by one point. As you may notice in our results, to date, in such a project, this is a technical issue, maybe more bound to the construction of the project. We need to have a correct sample to test this amelioration in biodegradation. And we have to, for us, in our case, we need to reserve a lot of soil for the lab experiment, for the pilot experiment, and for the full-scale experiment during around 2 years on the site, waiting that searcher, that project is going ahead to the correct step. And so it's very long, and you can't change the sample. And a good candidate as a sample need to be biodegradable, but not too much. If you have a sample that is impossible to biodegrade by bacteria or classical biopile and also by fungal inoculation, you won't see anything. And in our case, we have the opposite, that mycoremediation biodegrades, but also the control is only wild bacteria or maybe some fungus also coming from the straw. We saw a lot of coprinus. It's not inoculated, but in our case, we saw them. So there are some fungus coming from the straw, from the inoculum, from the miscanthus or whatever we put in the mixture. And so the difference is very, very slight. Both have steep slope of degradation, but to demonstrate that there is a difference between microinoculation and classical stimulation is hard. So you have both level, the limits, not too easy, not too strong, too hard. And when it's started, it's hard to make a U-turn and start all over the second project.
Yes, I would like to add something. For instance, all the laboratory scale experiments have really good efficiencies, but when you try to scale up, you found out like heterogeneity in the soil regarding the pollutant distribution, plus the microbiota distribution, plus other stuff that you didn't find out in the lab scale experiments. And also the static biopile, it's already developed, but we have to adjust to our requirements. And even only with 3 sites, we also found different key factors controlling mycoremediation. For instance, in Spain, it's humidity, but regarding the mesocosm of Italy, it was the aeration, one of the critical issues. And the clay content was 90%, I think, or clay and lime. So several issues, not only technical, but it's a thing regarding bioremediation and natural-based solutions that at lab scale or mesocosm scale works, but you won't try to go to the real field. It's different. And
I would like just that. Andrea, as you know, a lot of work on the field has to be done before to take a technology from the lab to the mesoscale to the field. We know that biopiles are over exploited, but micromediation is too young. So I think there is an opportunity. We need to the gap is there, is to test it more at the field and find out which are the real critical points to upgrade, like humidity, like aeration, like survival of the fungus at high temperatures, of which kind of fungus. Maybe there is a lot of issues that we have to solve.
Good questions that provoke a lot of answers. Ilaria and Rafa.
Ladies first. So for us, for example, when we try to do the biostimulation, we try to biostimulate what was the. Okay. So we try to biostimulate the fungal community. So we choose a bulking agent that was that was closer to the fungal growth substrate in order to stimulate that part of microbial community. And also, how Fiora said, there are many things that they need to be improved, and one of the tools can be a model, something that can be done in silico. And for that, also for the metagenomics and whatsoever, for fungi, the road is really more difficult than bacteria. So for that, we need more insight, we need more research from that, and metagenomics has to be balanced to what we want to do, in my opinion.
Yeah, I really want to answer the part of your question that was why mycoremediation if bioremediation is established. The point is in the title, is a step further in bioremediation. Is when bioremediation itself is not enough, just to add just another technique to be able to remediate soils that conventional bioremediation is not able to. So that's the problem. There are several contaminants that the bioremediation itself is not able, and we use mycoremediation, which is inside bioremediation, but that's the point of the project. It's like go further. And that is the main point and the aim. Of course, we are facing several issues, but you know, we are establishing a new technique, so that is part of the experience.
And one point of the upscaling, we noticed that it's not like in a liquid form, it's not homogeneous, and you have dimensional, that's maybe depth, width of the pile, and as Rachele said, you can't notice compaction in a beaker in a lab because the samples are too small. What we are sure that the fungi are able to eat the straw. So if your bulking agent is a straw, they will transform, and after 6 months you have no piece of straw more in your sample, in 1 ton sample. And in one, we noticed it was all transformed into something like very sticky liquid, making the soil, sticky, slippery, even if there were 2 points of water less than the other sample, because we stopped wetting it because it appears very wet. It was just because it makes a glue from the destruction of the organic compounds. And that's very hard to show in small sample and only happen in a scale-up.
Thanks. And to emphasize on what has been said before, so let's consider the big picture. So far what we are achieving with this project is to demonstrate that the implementation, the upscaling is feasible. Production can be mastered using mature production tools, which we can exploit for this purpose. We saw also with the implementation on site that with the logistics and the materials, the equipment is quite similar to what people know and use for classical bioremediation. So this is feasible. So we reached an MVP and now is about pushing it further, optimizing it, fine-tuning it, because when we talk to other remediation industrials, usually bioremediation is something that works nicely on sandy soil, but there's a but. They are stopped for certain soil types, for certain contaminations, and this is where the link between all the knowledge we have and what we see as data has to be made to have like a tool that helps us reduce uncertainty. That's what matters for any bioremediation technique, is to lower this uncertainty, which will deliver then the results, the targets for the industry. And that's really what we are working on now, to connect all these data and know how to guide the system. That's the main thing.
Is there another question in the room? And then I'll go back to Ivan.
Sorry. This is working? Yes, it is working. Okay. So very, very nice results, very interesting results. And but just a connection to a question of Andrea, that is about biopiles and based on bacterial metabolism. I think that an upgrade of the biopile approach was the dynamic biopiles instead of the static biopiles. So I'm wondering if you are thinking about what you said. I mean, you are trying to figure out all the parameters that has to be taken in consideration to transfer the technology on the real scales. And so, but this homogeneity of the soils might be, is a question. Are you thinking about moving the technology and testing the technologies, also thinking about dynamic biopiles instead of static biopiles, even though I know which is the principle at the base of the static biopiles. I know very well that is the fungal metabolism, but just to, I mean, to figure out this possibility to overcome some limits of the static one. Thank you.
So this is something we are looking at, but this is outside the scope of this project. We are testing it, and at least in terms of implementation, both approaches have their pros and cons. So if we're talking on-site treatment, static could be interesting. It means you have space, you have time. You can control aeration, but okay, you need to have the equipment and it takes time to implement. While, for example, at a soil treatment center, you could have a dynamic pile which you can move around depending on the logistics and the need of the platform. And so this can also be interesting. So yeah, if you take these two types of implementation, if you take them into account and fit them into the guiding tool, then there might be ways to conduct them both in the target we seek. So, and it also depends on the strains you use, if you bio-augment it with a specific strain, or if you count already on the fungal microbiota that is already present. So we can't rule this out as the dynamic system, because it might be that it's fine to just work with the microbiota there.
Yes, so we tried with the two demonstrators for the dynamic, with one demonstrating one the mesoscale, and what we could see at least for the mesoscale is also depends on the soil. For example, the soil that we had in LIFE MySOIL was too sticky to really have a dynamic condition that would work, and also it depends, I guess, on the strain, because some strains are actually, when you disrupt, they are disrupted, and some other strains actually are announced when they are disrupted. So I guess that it depends on the strain. There are some data on literature that says that disrupting actually helps the degradation and the growth. And so I think it's something that to take in account, but with the proper knowledge, let's say.
Hi, good morning. Well, I'm in the MySOIL project too, just in the University Autónoma of Madrid, and I'd like to answer and try to support one additional information to this question, because as Jorge from Kepler explained, we are just trying to work in a combined system. So starting with the dynamic, just trying to do a biostimulation from the own microbiota from the soil that is really strong, especially in our case. And then after a support of surfactants, and then changing to the static biopile. So it's possible, and it's a strategy that we are also exploring in this project. So, but still we will wait with what's happened with this both combined strategy.
Ivan, do you have any question from the chat that's stimulated by the exchange in the room?
Yes, we have some questions from Giulio Zanaroli from the University of Bologna. He wants to know if
Keep your microphone very near from your mouth, because it's going up and down.
Okay, now it's better? Okay, so yeah, Giulio Zanaroli from the University of Bologna. He wants to know if do you have information on how much homogeneously the inoculated fungi in the mesocones and in the pilot colonized the soil.
Push your microphone in front of your mouth. Sorry, push your microphone in front of your mouth. Yeah,
okay.
Because we hear the introduction, but not the question.
Okay. Do you have information on how much homogeneously the inoculated fungi in the mesocones and in the pilot colonize the soil?
He means observation.
Yeah, actually, there's 3 questions in the message. He wants to know. He has seen that we have inoculated the mesocones with single or multiple layers. He was wondering if this makes a difference in colonization and degradation.
Is there some difference between the way of inoculation? Maybe we made several repetition, big layer, thin layer, mixed, to check if this is important.
Yeah. So it's why spend mushroom substrate is added as layer in the pile instead of being mixed more homogeneously with the soil?
Okay. I try to answer. The reason why we decide to build up layers of soil and layers of Pleurotus alternated each others is because for what we know at the beginning, the Pleurotus has some problems of disturbance. We know that from the microcosm that Alessandro and his colleagues from Latouche realized, and so the fungal growth was inhibited with the disturbance of the matrix. So we decided to make layers, separate layers, that to avoid this problem in the full scale setup. This obviously depends from the kind of fungus. This is correct with Pleurotus. It's not the same, for example, I think with Agaricus. Maybe Alessandro or anybody there wants to.
besides our personal experiences, the scientific literature clearly witnesses the fact that especially basidiomycetes are extremely sensitive to mechanical manipulations. This is the reason why a static biopile configuration is preferred. And I think that is an excellent idea of the Spanish group to organize the full-scale biopile process in a phase 1 with a dynamic biopiling, but in the absence of the inoculant, followed by a proper mycoremediation process. So the reason is very simple.
Jofre?
All right. I will say also we are investigating this in the replicability tests. But the thing is, if the soil is too sandy or the soil is too clayey, maybe it's better to mix the amendment in order to increase the porosity in the case of clay soil or increase the fill capacity to hold water in the case of the sandy soil. But if it's like suelo franco, in English, it's okay, frank soil, or like the mixture between loamy soil. Sorry about that in my Spanish. The proportion of clay, silt, and sand, it's quite good. Maybe just with the big layer, it's enough. And the other, one part of the question was regarding the thin layers. The thin layers, what happened is that the compactation makes not good porosity for the fungi to grow, and that's it. One small short question before going to lunch.
Is it another one, Ivan?
No. This was the last one.
From the room? Yeah, it's sure to answer different question. That's this is one point we have to discuss. Everybody of us, at least, and maybe other people in the room, know that the potential of fungus is able to degrade pollutants. All the question is how to upscale, how to domesticate them, as I told to Novobiom 3 years ago, maybe. We know it's working. Is it better to put them quiet as they are working in the forest with a very good efficiency? But how to industrialize this type of soil? So is it better to make a mixture? Because we know for classical biodegradation, it's better to each week or each 2 weeks to mix and put in contact zones where they are not in contact, because you need to have the substratum, the fungus, the pollutant, and the air, the nutrients, and all. And each time you mix, you upgrade your homogeneity. But is it a good way to grow fungus? Nobody grows fungus like this. So we have to test both.
Just a provocation. I think that the most innovative approach to mycoremediation would be to make it independent from excavation. So actually it is an ex situ techniques. But so I think that some efforts should be spent toward converting it to an in situ technique. Some researchers have attempted to do the job. For example, there is a Finnish researcher, and I apologize, I do not remember his name. He created some wells along some contaminated areas, and within these wells introduced some pools with colonizing fungi. The problem is, however, that fungi require the presence of organic matter in the soil. So their colonization is strictly dependent on that. So probably there should be also a search towards fungal strains or fungal groups, the colonization of which is independent on the presence of lignocellulosic amendments that actually seems to be a needed prerequisite to do the job.
I think we have done just in time. Half a minute, Enrique? No? Simona?
I wanted to say that actually we started to do an in situ treatment with fungi, but unfortunately they were based on ascomycetes. And the nutrients that we added, because Alessandro is right, they need organic matter, and so they have to be supplied anyway with organic matter. But anyway, we did it with ascomycetes on TPH and pH, contaminated soils, and in situ application that is an engineerized one, so it's quite complex too. But anyway, there are some news about this. But Alessandro is right; they do not live only on the contamination; they need substrates to work on. Unfortunately, yes, you're right. Sorry.
So many thanks, and I will give back the floor to Fiora to conclude.
Thank you to everybody one more time, and for those of you that will join us at the site, at the visit site, the site visit. Sorry, we will go from here at 14:30. So we have 1 hour and a half, 1 hour for lunch, and half an hour to collect ourselves and go to the bus. I think will be enough. So I would like to thank you all the colleagues, all the companies, all the universities, everybody who have the opportunity to help to this project, and that's it. Every other question you have, you can address us to us at the site visit. Okay. See you later. Valentina will show you the way to the lunch.